Hi friends, a comet from another star rushes inward through the deep cold, trailing a faint veil of carbon dioxide and dust. The sun brightens and grows restless as dark spots multiply on its face and tendrils of magnetized gas erupt into space. On Earth, the ground shakes in many places at once. Phones chime with quake alerts. Skies at night glow with aurora far from the polar circles, while pilots and farmers struggle with navigation errors. The question rises with a sense of urgency and skepticism in equal measure. Are these strands connected? Has a visitor from another sun stirred our star and set off an increase in earthquakes? Or are we seeing patterns where none exist? The only honest way forward is to follow the evidence and let the data speak. The interstellar comet, now known as 3I Atlas, appeared in early summer of 2025 as a fast-moving speck in a wide-field survey camera in the Chilean desert. Follow-up observations and pre-discovery images showed a path and speed that no object born in this planetary system could sustain. The orbit is not bound. It is open to the galaxy. Its closest approach to the Sun will be just inside the orbital distance of Mars in late October. Then the comet will depart toward deep space and not return. The National Aeronautics and Space Administration confirmed the object poses no threat to Earth and that it will remain at least 1.6 astronomical units away. The name honors the asteroid terrestrial impact last alert system that found it. The simple facts are striking. This is only the third known interstellar object to pass through our neighborhood, and it offers a rare laboratory for learning what other planetary systems make and lose to the dark between stars. In the weeks that followed discovery, the Hubble Space Telescope and the James Webb Space Telescope joined forces on the new arrival. Imaging from Hubble on a July observing run revealed a tear-shaped coma wrapped around a hidden nucleus only a few kilometers across. Spectra from the James Webb Space Telescope in early August found that the gas surrounding the nucleus is dominated by carbon dioxide, a composition clue that may point to how and where the comet formed in a protoplanetary disk around a distant star. These are not just pretty portraits. They are measurements that let chemists and dynamicists estimate the age and birthplace conditions of material that has never felt our sun until now. The path of this interstellar traveler also placed it within reach of robotic observers in orbit around Mars. Mission planners at the European Space Agency readied instruments to catch its passage by the red planet in early October. The geometry is not close in a neighborhood sense. The distance will still be tens of millions of kilometers, yet even at that range, professional instruments can extract color, composition, and dust production rates that refine models of the nucleus and coma. The more vantage points, the more complete the three-dimensional picture. While telescopes were turning, the sun was having a season of its own. The 25th numbered cycle of solar activity rose faster and higher than early forecasts expected. In May of 2024, Earth rode through the first extreme-level geomagnetic storm in over 2 decades. Auroras swept across continents to places that rarely see them. Radio communication degraded. Precision farming had to pause in some regions when centimeter-level positioning went astray. Grid operators watched transformer behavior and voltages with unusual attention. Analyses by the National Oceanic and Atmospheric Administration and the North American Electric Reliability Corporation documented the event and placed it in historical context. The storm was powerful but manageable, an important reminder that space weather is not a curiosity. It is a practical hazard that modern societies must learn to live with. Public interest spiked with each new solar flare, each new earthquake, and the camera-ready beauty of interstellar ice turning to gas. It is human to weave a story from bright threads, but do the numbers support the idea that earthquakes are multiplying? The long record compiled by the United States Geological Survey offers a consistent baseline. Over more than a century of global monitoring, the world can expect on the order of 15 earthquakes of magnitude 7 or greater in an average year and about one event of magnitude 8 or greater. Some years exceed the average and some fall short. That ebb and flow does not indicate that a very large earthquake is imminent. It is simply the way the planet behaves when stresses accumulate and release along faults. In total, the National Earthquake Information Center now locates roughly 20,000 earthquakes in a year worldwide, or a bit more than 50 events per day. Most are too small to be noticed, and many of them are detectable only because instruments and algorithms keep improving. What used to pass in silence is now charted in detail. Dense arrays of seismometers, cooperative global networks, and new pattern recognition methods leverage the power of thousands of sensors and billions of phones. The global seismographic network continues to provide high-quality reference measurements. Regional networks create the fast situational awareness that responders need. Machine learning has lowered the magnitude of completeness in some catalogs, bringing faint events into view that once would have been missed. Even smartphones now contribute through distributed early warning systems that detect the first quick waves and push alerts to communities seconds before the slower and more damaging shaking arrives. This is why the line of detected small earthquakes climbs over the decades. The ground has not changed as much as our ears have. So if the count of small events rises because we are getting better at listening and the count of large events wanders around a stable long-term average, where does the idea of earthquake multiplication come from? Some of it comes from the natural tendency to connect things that happen at the same time. A solar storm makes the sky glow where it usually does not. A large earthquake strikes in a different part of the world a few days later. The match is vivid and feels meaningful, but the physics and the statistics are not impressed by coincidence. The internal engine of the Sun operates on magnetic fields generated by flows in its plasma, differential rotation wraps and shears field lines. Convection rolls twist and shuffle them. Slow circulations move heat and magnetic flux toward and away from the surface. Together, these processes build the 11-year cycle of spots and flares and the 22-year magnetic polarity cycle. This is a deep internal dynamo, not a system that a passing comet can switch on. Claims that comets can trigger flares have appeared over the years when a sun-grazing object and a coronal explosion happen close together in time. Careful analysis shows that proximity in time does not imply causation. The apparent link fades under scrutiny. Solar eruptions are rooted in magnetic stresses that build and release within the solar atmosphere. No credible mechanism has been found by which a small icy nucleus far from the surface could unlock that stored magnetic energy. The better interpretation is that flares happen frequently during active phases of the cycle, and occasional coincidences with comets are expected by chance alone. If the Sun is not being switched on by an interstellar visitor, why has it been so busy? In late 2024, the National Aeronautics and Space Administration and the National Oceanic and Atmospheric Administration reported that the Sun had reached the maximum phase of its present cycle. The auroras of May 2024 fit that picture of high activity. The numbers of spots and the strength of flares in 2024 and 2025 have tested and updated predictions that were made early in the cycle. This is the kind of scientific self-correction that grows knowledge. Models are only as good as the data they have seen. As new data arrive, forecasts adapt. That does not require a comet. It requires the Sun being a complex fluid plasma star, which is exactly what it is. Still, the search for connections is not pointless. It just needs to focus on the places where physics permits a lever. Space weather can push on Earth in several well-understood ways. When a coronal mass ejection drives a shock into the magnetosphere, currents flow along the magnetic field into the auroral ionosphere and across the polar caps. The ring current strengthens and the global magnetic field at Earth's surface changes over minutes to hours. Those changes induce electric fields in the ground. On long conductors like power lines and pipelines, those fields drive quasi-direct currents that transformers were not designed to carry steadily. Grid operators watch transformers for signs of saturation. Pipeline engineers track corrosion risks that increase when induced currents alter the chemistry at metal surfaces. These are not exotic effects. They are textbook results of Faraday's law applied to a planet-sized conductor wrapped in a changing magnetic field. The May 2024 storm offered a recent and vivid demonstration. Operators across North America and other regions reported induced current levels and harmonics that stressed some equipment. Protective systems acted and the bulk power system remained stable, a success owed to preparation and training. At the same time, the upper atmosphere heated and expanded. The thermosphere grew denser, increasing drag on thousands of low Earth orbit satellites. Teams that track objects and assess collision risk had to account for the changed environment as many spacecraft dropped faster than usual and debris populations decayed. Spacecraft operators know these episodes well. They practice them, but the size of the storm made the choreography visible to the public. Navigation and timing systems also felt the storm. The global positioning system depends on signals that travel through the ionosphere, whose electron content changes during storms. When the total electron content shifts quickly, the errors grow, and centimeter-level agriculture and surveying cannot hold a straight line. Ionospheric scintillation can break lock on signals and force users to pause or fall back to less precise modes. Regulators and weather agencies documented these impacts and solicited reports to learn where the vulnerabilities lie. Models that estimate storm time ionospheric departures from normal conditions help, but they cannot entirely eliminate error in severe storms. This is why planning across sectors now includes space weather scenarios alongside floods and fires. Space weather can also leave fingerprints on the ionosphere during earthquakes. Several satellites and dense ground networks have detected traveling disturbances in the ionosphere that follow strong shaking and tsunamis by minutes. Those disturbances are physics at work in the atmosphere and ionosphere. Acoustic gravity waves launched by rapid ground motion and by large ocean waves ripple through the air and modulate electron densities hundreds of kilometers above the surface. The question that continues to invite research is whether there are reliable and repeatable ionospheric anomalies that precede large earthquakes by hours or days under quiet space weather. Some retrospective studies show intriguing patterns over limited regions and times. Others emphasize how difficult it is to separate earthquake-related signals from the complicated background created by the sun, the magnetosphere, and regular meteorological processes. The community now designs experiments that use multiple independent measurements to reduce false positives and to test models prospectively rather than only after the fact. A related line of inquiry examines whether geomagnetic storms can slightly increase the likelihood of earthquakes in the weeks that follow. The proposed mechanisms include changes in crustal stress through electromagnetic induction, piezo-magnetic effects in certain rocks, or subtle changes in pore pressure if currents convert to heat in conductive fluids at depth. This is a challenging topic because earthquake occurrence is noisy and strongly clustered by nature. Yet some recent statistical studies have reported an increased likelihood after intense storms at specific lags on the order of 4 weeks. Even authors of those studies caution that correlation is not causation, and that any effect, if real, is small compared to the main drivers of tectonic strain. That is the right level of humility. Research continues. Culture-wide claims that a comet woke the sun, which then multiplied earthquakes, do not belong in this careful conversation. To keep the story anchored, it helps to revisit what actually generates most earthquakes. The outer shell of Earth is broken into plates that move at speeds of centimeters per year, driven by heat from the interior and the sinking of cold slabs. Plates slide past one another, collide, or pull apart. Friction and locked patches build stress until the rock fails and slips. That release launches seismic waves that travel through the planet. Faults do not need the sun to tell them when to break. They obey the physics of friction and fracture. Local triggers can matter in special cases, such as human activities that alter pore pressures or volcanic intrusions that pump magma into crust. But even then, the timing of most large tectonic earthquakes reflects long build-up and local fault conditions, not conditions in space. The broad global patterns confirm that rule year after year. With that framework in place, the evidence about 3IATLAS falls into perspective. This comet is an extraordinary opportunity for comparative planetology. It has already given astronomers chemical clues in the carbon dioxide, rich gas surrounding its nucleus. It will cross the plane of the inner solar system and offer a few months of high-value observing windows from multiple spacecraft and ground observatories. It will not come close enough to exert a gravitational influence on Earth or the Sun that is measurable. It will not intersect any of the dominant magnetic structures that give rise to flares. It will not seed the corona with dust in ways that could change a global cycle. What it will do is remind us that planetary systems share materials across the galaxy and that our instruments are now good enough to catch and study these gifts when they appear. The Sun, proactive and indifferent to storytelling, is doing what solar stars do. It is winding down from a strong crest in its 11-year cycle. Another crest will arrive in the next decade. Another visitor from another system may arrive in this century or may not. Space weather will continue to matter for satellites, aviation, exploration, and power grids. The point of the May 2024 lesson was not doom, it was practice. Grid planners coordinate with space weather forecasters. They use models and measurements to anticipate transformer stress and to adjust operations when the ionosphere becomes electric and dynamic. Air traffic management and polar route flights look at radiation, communication, and navigation. Satellite controllers use density estimates to anticipate drag and to schedule station keeping. This is the ordinary craft of a technological society. Back on the ground, the answers to the multiplication question will continue to come from catalogues and from the people who maintain them. The United States Geological Survey and partner agencies around the world keep the record straight. They count and locate, review and revise, and publish simple baselines that anyone can check. On average, the planet delivers about 15 magnitude 7 events per year and 1 event of magnitude 8 or larger. In a typical year, the National Earthquake Information Center catalogues about 20,000 earthquakes of all sizes. That reality does not make headlines, but it is the measure by which new claims must stand or fall. As more sensors are deployed and as algorithms learn to separate noise from signal with greater skill, the smallest events will continue to grow in number on our charts. The ground beneath did not speed up. Our ability to hear it did. None of this diminishes the wonder that a comet from another star can inspire or the value it brings to science. Consider one more number turned into words to keep faith with clarity. The nucleus size estimates for 3-Dark-Eye Atlas range across a span of a few kilometers rather than tens of kilometers. A body in that size class, at distances of tens of millions of kilometers, exerts a gravitational tug on Earth so small that it disappears under the sway of the Moon and the Sun. During the weeks around perihelion, the comet will absorb and re-radiate sunlight, release gas and dust, and draw graceful lines in the solar wind like a windsock in a high-altitude stream. Instruments will translate those lines into densities and flow speeds and particle sizes. Later, when the comet recedes and the data mature into peer-reviewed papers, its most important legacy may be in the fine print of chemistry. Ratios of carbon-bearing molecules. The relative absence or presence of nitrogen-bearing molecules. The mix of rocky grains versus fluffy aggregates. These comparisons reveal the temperature and pressure of the nursery, where the comet formed and how long it has been wandering. At the same time, the years surrounding this solar maximum will refine our risk models. The May 2024 storm tested every capability. It revealed where models of the ionosphere need improvement and how thermospheric heating and cooling times control drag estimates. It quantified where and when induced currents in long conductors spike. It broadened the public understanding that space weather is not only an aurora show, it is a driver of errors in timing and positioning. The agencies that monitor the Sun and the magnetosphere now circulate after-action reviews that feed directly into procedures for the next storm. That is how resilience grows. There remains one more thread to tie down. The possibility that geomagnetic storms could nudge earthquake probabilities very slightly in certain places and times deserves to be explored with care. A small effect, if repeatable with independent datasets, would not overturn the fundamentals of tectonics. It would add a nuance to local hazard models. A recent analysis that found increased likelihoods at lags near 4 weeks after intense storms is a prompt for deeper study. It is not a warrant for sensational headlines. Robust tests across multiple regions, catalogues, and methods will be needed to establish or refute any such effect. Until then, the most accurate short phrase we can use is the simplest. The evidence is not settled. Everything we have learned in this moment can be put to work. Viewers who care about accuracy can hold 2 facts at once. First, 3I Atlas is a genuine interstellar messenger that has already delivered valuable measurements. Second, the Sun is active because of its own internal physics and journey through its magnetic cycle. These truths are compatible, and they exclude the notion that a comet woke the Sun and multiplied earthquakes. The world remains beautiful and hard-headed at the same time. Understanding this does not make the story dull. In fact, it makes the story richer. It lets us pay attention to forces that do connect the Sun and Earth in reliable ways, electric currents that flow in space and close through the polar ionosphere, the ring current that waxes and wanes and leaves a signature in global indices, the induced currents that circulate through grid conductors and pipelines when the geomagnetic field swings hard, the neutral air that swells in the thermosphere and brushes the orbits of satellites, the electron content that bends radio signals and shifts clocks and positions when we need them to be steady. In every case, the physics is known, the measurements are there, and the work of mitigation continues. The months ahead will bring a final burst of attention for 3I Atlas as it reaches its closest point to the Sun and then fades from view. Instruments around Mars will attempt a distant look. Ground-based telescopes will squeeze as much resolution and spectral data as they can from the time and weather they get. The James Webb Space Telescope may take another crack at its chemistry before the geometry becomes unfavorable. Then the Sun will hold center stage again, as it always does. Alerts will continue. Drivers will glance up at aurora forecasts. Air crews and controllers will plan around radio blackouts near the poles when they appear. Power system operators will run drills and apply lessons learned. None of these routines are dramatic in the way that a speculative causal chain can be, but they are the hard work that keeps cities lit and planes moving and maps accurate. If we measure success by honesty and depth rather than by volume, the answer to the central question reads like this: earthquakes are not multiplying because a comet from another star awoke the Sun. Earthquakes are doing what earthquakes have always done. The Sun is doing what the solar cycle dictates with a vigor that has surprised some forecasters and delighted heliophysicists. The comet is a gift for comparative chemistry and dynamics. The genuine connections between space weather and human systems are more than enough to justify the attention they receive. They are also more useful than any invented link. When the ground shakes, build better and prepare well. When the Sun storms, harden systems, improve models, and keep learning. The story is not smaller for being true. It is simply more solid underfoot. Deep inside the planet, heat rises in slow columns and sinks in cooler sheets. The surface is broken into giant pieces that slide, grind, and dive. Think of a machine with plates as the moving parts and the mantle as the conveyor of energy. The engine is simple in concept and complex in detail. Hot rock expands and becomes buoyant. Cooler and denser rock sinks under its own weight. That circulation drags plates apart at ridges, shoves them together at trenches, and lets them scrape past at transforms. Where plates meet, the crust fails along fault zones that lace continents and oceans. That failure is the core of earthquakes. To understand why the count looks like it rises and falls, we must see where the system stores energy, where it releases energy, and how it sometimes masks or amplifies what we think we are observing. Ocean ridges are the seams where new crust forms. As magma from the mantle rises and cools, it creates bands of basalt that move apart like a slow conveyor belt. Earthquakes here are usually shallow because the brittle layer is thin near hot upwelling. Their magnitudes tend to be modest. Even so, they teach us about the friction of rock and the texture of the newly minted ocean floor. Far away at subduction zones, the story changes from modest to monumental. An oceanic plate that has cooled for tens of millions of years becomes dense enough to sink back into the mantle. It bends downward at a trench and drags along the edge of the overriding plate. Between the two plates lies the megathrust, a contact that may lock for centuries, then release in a few minutes with the force to lift or drop the seafloor by several meters. These are the sources of the largest tsunamis and the most powerful ground motions recorded by instruments. Along the margin, the contact dips into the earth, and a band of intermediate and deep earthquakes marks where the sinking slab continues to fracture and deform to depths of hundreds of kilometers. Those deep events do not generate tsunamis, but they reveal how solid rock can fail under immense pressure and temperature through phase changes and transformational faulting. Continental collisions tell a different story. Where two buoyant plates meet, neither wants to dive. The crust thickens and rises to form ranges that reach the highest elevations on the planet. Faults within the growing mountain belt crisscross like a shattered windshield. Some faults accommodate horizontal shortening by thrusting. Others allow crustal blocks to slide laterally and even to stretch in local basins that open behind ranges. Earthquakes here can be very destructive because they occur beneath populated plateaus and valleys. The geometry is complicated, the faults are many, and the time between large events on any single structure can be long enough to fade from local memory. That long quiet is what turns hazard into risk. Transform boundaries, the places where plates slide past, are laboratories for understanding how faults behave along their length. Some sections creep almost constantly. You can see curbs offset across the fault by a few millimeters each year, like a slow-motion magic trick that never stops. Other sections lock and store elastic strain for decades before a large release. Both behaviors may happen along the same fault, with creeping reaches bracketing a locked asperity. The juxtaposition of steady motion and pent-up energy shows that the physical conditions in the fault zone vary significantly over short distances. Temperature, pressure, mineralogy, and the presence of fluids all change with depth and a long strike. That mosaic explains why one town may experience frequent small events while another waits through a quiet that ends with a damaging shock. Fluids are the subtle agents that change how rock breaks. Water released from minerals in a sinking slab rises into the overlying mantle wedge and lowers the melting point, helping to feed volcanoes along the arc. The same fluids can migrate into the plate boundary, raise pore pressure, and reduce the effective normal stress that keeps a fault locked. If the pressure grows high enough, sliding begins at lower shear stress than dry rock would require. In the shallow crust, even small changes in pore pressure can modulate seismicity. When fluids escape from deep formations through natural pathways or human-made wells, they can trigger swarms of small earthquakes by unclamping faults. At greater depth, metamorphic dehydration reactions within sinking slabs may generate isolated bursts of seismicity. In every case, the fluid does not create energy out of nothing. It lowers the barrier to release the energy that tectonics has already stored. Not all earthquakes are alike in the way they start and grow. Slow slip events spread over days to months, releasing energy so gently that people do not feel them. They happen at the edges of the locked zone, mostly at depths too great for brittle friction to behave in the usual stick-slip manner. Slow slip can load the shallower locked part of a megathrust, nudging it toward failure, or it can ease stress without causing a damaging event. Tremor, a faint and persistent vibration of the crust, often accompanies slow slip and maps out where fluids and ductile conditions prevail. In contrast, dynamic ruptures of damaging earthquakes outrun a racing car in speed and sometimes move so fast that the rupture front exceeds the shear wave speed of the rock, a phenomenon called supershear that can generate large stress concentrations at the rupture tip. Between these extremes lies a spectrum of behaviors that connect deep, ductile flow, transitional slow slip, and shallow, brittle fracture. As the clock ticks down to a major rupture, stress changes at the fault core pass a point of no return. The physics is not mystical. It is the same dry-sounding but powerful rate and state friction that laboratory experiments have mapped out for decades. At low slip rates and with certain mineral mixtures, the interface strengthens with time. That property helps faults stay locked between events. Under other conditions, the interface weakens with slip, creating a positive feedback loop. Once a patch begins to slide, it becomes easier to keep sliding. A critical nucleation size dictates whether a small slipping area will stop or will grow into a full rupture. Think of a patch of snow on a slope. If the sliding region is smaller than a certain size, friction and geometry slow it to a stop. If the patch grows large enough, gravity and low friction carry the failure across the slope. In rock, the nucleation length depends on effective normal stress, which reflects pore pressure, and on the elastic stiffness of the surrounding material. When natural variations or external perturbations push a locked patch past the nucleation threshold, a rupture can organize and run. The minutes before strong shaking reach a city often pass quietly. Deep within the fault zone, micro cracks begin to link. Some appear as tiny earthquakes, but most are too small to register. The rock around the main future rupture dilates slightly as cracks open, lowering fluid pressure locally and changing the way waves would travel if we could measure them perfectly. This dilatancy and the later diffusion of fluids back into the open space were once hoped to be reliable precursors. In practice, the hydrological and mechanical signals are subtle and buried under natural variability. When the unstable patch finally runs, the first energy to escape are compressional waves that travel fast. These primary waves shake buildings gently and rarely damage structures. Shear waves follow and carry the destructive power because they move the ground side to side and up and down. The rupture front carves through rock at speeds of kilometers per second. Slip on the fault may reach several meters in a few seconds, converting stored elastic energy into seismic waves, heat, and off-fault cracking. The pattern of strong and weak shaking that people experience depends on the direction the rupture front propagates, the sedimentary basins that trap and reverberate waves, and the geometry of the fault itself. Two towns at the same distance from the epicenter can have different damage simply because one sat in the path of directivity and the other did not. Foreshocks sometimes pepper the hours or days before a large event. They attract attention after the main shock because they stand out on a plot viewed with hindsight. The problem we face in practice is that small earthquakes are common, while only a tiny fraction are true foreshocks. Most bursts of small events fade without a great release. If we declared an imminent alarm every time a cluster appeared, we would be wrong almost every time. When a small event precedes a large one by minutes on the same fault patch, it may reflect the very last steps of nucleation that no public warning system can exploit. Speed is the enemy. The rupture takes off too quickly and grows too fast for a human-centered decision loop. That is why early warning systems do not predict. They detect the primary waves and compute the expected shaking from the already started event. Animals, gases, lights, and ionized air have all been promoted as harbingers of earthquakes. The stories are vivid. A village of toads abandons a pond days before a main shock. Dogs bark all night. Birds rise in a panic. The explanation offered is that animals sense something we do not. Sometimes they respond to small shaking that instruments barely catch, which is a kind of last-minute early warning filtered through biology. Sometimes they respond to changes in groundwater, odors, or electromagnetic noise created by local weather or human activity. The challenge is consistency. To become a tool, a precursor must be reliable, testable, and useful. Anecdotes do not pass that bar. Controlled studies using tagged animals and continuous monitoring often show that unusual behavior is as likely on quiet days as it is before an event, once you account for how many days and animals are observed. Radon emissions have been proposed as a chemical alarm because radon is produced by the decay of uranium in rocks and can move with groundwater or along microcracks. If a fault zone dilates before failure, perhaps radon could vent in unusual amounts. Investigators have indeed recorded spikes in some places before some earthquakes. They have also recorded spikes linked to changes in rainfall, barometric pressure, and human pumping without any seismic consequence. The same sensor may be quiet before a later, larger event in the same region. The combination of multiple influences and local geology produces a background that is too noisy for operational prediction. As a research topic, radon variations remain interesting because they might reveal properties of fault zone permeability and stress. As a public alarm, they remain unreliable. The upper atmosphere adds one more alluring path Receivers that depend on radio signals passing through the ionosphere can infer how many free electrons are in the way. Some studies have reported shifts in the total electron content before large earthquakes, especially over subduction zones. Those signals, however, live in a stormy sea of change driven by solar radiation, by tides in the upper atmosphere, by geomagnetic activity, and by lower atmosphere weather that pushes waves upward. When space weather is noisy, it can mimic the patterns that earthquake-centered papers look for. When space weather is calm, the ionosphere still varies over the day and over seasons. Separating a true pre-seismic signature from this shifting background requires multiple independent instruments, careful statistical controls, and prospective testing. The field is moving in that direction with networks that combine ground receivers, radio occultation from satellites, and magnetometer data. For now, the consensus remains that while earthquake-generated waves produce clear ionospheric disturbances after the fact, reliable and operationally useful ionospheric precursors before an event have not been established. Earthquake lights are perhaps the most dramatic claims. People describe silent glows, flickers, or sheets of pale illumination near the horizon before or during shaking. Video evidence exists for some events, but false positives such as electrical arcing from damaged lines and transformers are plentiful. One hypothesis suggests that stressed rocks can release charges that flow to the surface and ionize air, creating a faint glow. This mechanism might function in rare settings where the crust is rich in certain minerals and where the fault geometry focuses fields. Even if real, such lights would be rare and not a basis for broad prediction. They remind us that the Earth is full of fascinating physics. They do not give a clock we can trust. Because the public appetite for patterns is stronger than the supply of firm evidence, correlation and causation often get mixed. A chart with a rising trend becomes a headline even when the rise reflects detection thresholds that changed over time. A plot that aligns solar cycles with a handful of earthquakes persuades the eye while ignoring the many large earthquakes that occurred during quiet solar conditions and the many active solar months without large earthquakes. To navigate this, ask simple questions. Is the sample large enough to matter? Were the parameters set before the data were examined or after? Was the model tested on new data from other regions and other times? Did the authors account for aftershocks which cluster strongly in time and space and can masquerade as an increase in background rates? Did they consider magnitude of completeness, the smallest size at which a catalogue is reliably complete in the time window under study? If that threshold changes, comparisons between decades are not apples to apples. In addition, were results robust to different catalogue declustering methods? Could the visual impact be an artifact of the vertical axis choice, or of smoothing that erases quiet intervals? When these checks are applied, many breathless claims dissolve. A common trick in persuasive charts is to choose endpoints that favor a story. If a series starts with an unusually quiet year and ends with a busy year, the trend looks dramatic. If you roll the window forward by only a few years, the line may flatten. Another misstep is to combine dissimilar measures into a single index that hides the true drivers. Counting all earthquakes equally ignores the fact that most shaking damage and almost all deaths come from a small number of large events. A year with an unusual number of magnitude 5 earthquakes and no large earthquakes is not equivalent in hazard to a year with 2 great earthquakes. Whenever possible, insist on comparisons that weight by energy release or at least separate size classes. Also watch for undisclosed changes in instrumentation. The world now deploys ocean bottom seismometers, borehole sensors, and crowdsourced accelerometers that simply did not exist several decades ago. The detected count must rise for small events by the very success of these tools. That is progress, not a warning of planetary change. All of this careful thinking is not an argument to ignore risk. It is the foundation for practical action. Early warning systems now operate in several parts of the world. They use dense networks of instruments to detect the first compressional waves and compute a quick estimate of the expected shaking for nearby populations. Messages sprint across fiber lines and cell networks faster than the more damaging shear waves. The time gained is usually measured in seconds rather than minutes, but seconds are enough to reduce harm. Trains can brake, elevators can stop at the nearest floor and open, heavy industry can pause delicate operations, hospitals can protect a patient in surgery. School children can take the simple protective posture of drop, cover, and hold on. The key is automation and routine practice. People who have rehearsed will act without confusion. Engineering is the other pillar of readiness. The safest building is the building that does not fall. Modern codes do not aim to save every object within a structure. They aim to preserve life by preventing collapse. Reinforced concrete that is well detailed, steel frames that can form plastic hinges in a controlled way, and wood structures with strong connections all perform far better than their ancestors when the ground moves hard. Base isolation places flexible bearings between a building and its foundation so that the ground can move beneath while the structure above stays relatively calm. Supplemental damping devices act like shock absorbers to remove energy from the motion of the building. Retrofitting older buildings is a challenge because it requires investment, but the payoff is seen in reduced casualties and faster recovery. Soft story buildings, where an open ground floor under a heavy upper floors lacks stiff walls, are a known vulnerability. Adding shear walls or frames can transform performance. Unreinforced masonry with heavy roofs is another classic hazard. Tying walls to diaphragms and adding bracing saves lives. Lifelines deserve as much attention as buildings. Water mains, gas lines, electrical substations, and data centers are the organs of a city. Flexible joints on pipelines that cross faults, automatic shut-off valves that stop gas flow when shaking reaches a threshold, and substations that are braced and equipped with devices that limit the travel of insulators all add resilience. Bridges that cross rivers and bays need bearings and column jackets that allow controlled movement without collapse. Ports and airports, which connect a city to food and medicine, need contingency plans for cranes, runways, and fuel storage. A resilient community invests in these silent details long before a headline event. Preparedness is not only for institutions. Households can reduce harm with a few steps. Secure tall furniture to walls, latch cabinets that contain heavy dishes or chemicals, store water and non-perishable food for several days. Keep a flashlight and sturdy shoes near beds so that broken glass does not cause injury in the dark. Learn how to turn off gas if that is part of the local guidance. Agree on a family plan for where to meet if phones and data are down. Know the local hazard map, including tsunami evacuation routes if you live near a coast. Practice the protective posture so that it is automatic. None of these steps predict anything. They are common sense responses to a known hazard. When the focus returns to science, remember that measurement drives progress. More instruments on the sea floor will fill a major gap in our understanding of subduction zones where the largest earthquakes occur. Cabled observatories can stream data in real time, allowing early warning offshore and improving tsunami models. Borehole seismometers placed deep and quiet reduce noise and capture tiny signals that reveal how faults prepare and heal. Laboratory experiments on fault gouge materials at pressure and temperature close to natural conditions continue to refine the parameters of rate and state friction. Numerical modeling at high-resolution maps how ruptures navigate bends, step-overs, and branching faults. All of these efforts converge on a goal that is not prophecy but precision in hazard assessment. In the same spirit, space weather belongs in our planning, but not as a ghost story that animates faults. The real connections are already on the desk of engineers and operators. The sun emits bursts of particles and electromagnetic waves that change the magnetic field around Earth. Those changes induce currents in long conductors. Power systems measured those currents during the strong storm in recent years and adapted operations. Aviation altered routes around polar regions during radio blackouts. Satellite controllers accounted for higher drag as the atmosphere expanded. These are robust and practical links. They deserve investment and attention. They do not cause the crust to break along faults that were otherwise quiet. There is a final point that blends statistics with humility. The planet is large. Earthquakes of moderate size happen daily. Large earthquakes happen yearly. Great earthquakes, the kind that reshape coasts and tilt the axis by a fraction of a second of arc, happen a few times in a human lifetime. In such a crowded field of data, coincidences are guaranteed. A comet from another star will occasionally pass through the inner solar system at the same time that the sun flares and that the crust in some place finally yields. The alignment of dates does not add a force to a fault. When something unusual is proposed, the bar for evidence must be higher than a plot with two wiggly lines. It must be a mechanism that can be tested and a prediction that survives when tried outside the dataset used to build it. If we keep that standard, the path forward is clear. We can marvel at interstellar visitors for the chemistry they reveal and the formation histories they encode. We can track the solar cycle and prepare for space weather guided by data and models that improve each year. We can map faults, monitor slow slip, and refine early warning so that the seconds we gain are used to their fullest. We can make buildings and lifelines safer through engineering that is already proven in earthquakes that have come and gone. We can teach the difference between patterns that matter and illusions that do not. In doing so, we respect both curiosity and caution. When the next earthquake comes, it will come because tectonic stresses on a fault exceeded the strength of that fault at that moment. Instruments will feel the first compressional waves and send the alert. People will act as they practiced. Structures will behave according to the quality of their design and the care of their maintenance. Recovery will draw on the resilience that communities built in advance. Somewhere far above, The sun will continue its cycle, at times quiet and at times active. A comet will glide outward on its unbound path. None of these scenes require a conspiracy of causes. They are connected only by our habit of looking for stories. The better story is the one that puts each phenomenon in its place, linked where physics says they are linked and separated where physics says they are separate. So the closing thought is as practical as the opening question was bold. Earthquakes are not multiplying because of a visitor from another star. Counts change because our listening improves, because seismicity clusters by its nature, and because time windows can mislead. The sun does influence our technology and our atmosphere during storms, and we should continue to harden systems accordingly. Our task on the ground is to respect the fault zones under our feet, to strengthen the places where we live and work, to rehearse the few simple actions that protect lives, and to demand clarity in claims that arrive with dramatic music. The planet is a machine that runs on heat and gravity. It gives us warnings that are measured in science rather than in rumor. If we build on that foundation, the next powerful earthquake will still test us, but it will not surprise us.